What?
Okay, so let's do a little review here. Now, this is stuff that I know you've seen before here initially. We're gonna take a look at triangles primarily. That's sort of the focus of Chapter 4. We're going to take some of the relationships we've already discussed in Chapter 3, and we'll sort of move those into a new form where we're dealing with triangles in particular. So let's start off by discussing triangles. How do we classify triangles? There's a lot of ways that we can be specific about triangles and classify them. We can classify triangles by their sides or by their angles. For example, we'll look at those. And we want to, sort of at the end of this first little shot of stuff that we're looking at that corresponds to section 4.1 in the textbook, we want to be able to find all the angle measures of a triangle, for example. We're going to start off with the definition of a triangle. And this is, we all know what a triangle is, but this is a good chance to sort of correlate what you already know with the math vocabulary, because that's one of the things that we've got to start doing more and more. It's a sad fact that when you go to college, one of the main traits that predict success in college is the ability to read a textbook, because so much of what you do in college is driven by a textbook. And so, it's important to be able to sort of make these connections. Now, we all know what a triangle looks like. Let's connect it to this definition. A triangle is a figure formed by three segments joining three non-collinear points. Well, it makes sense. Three sides of a triangle. What's this non-collinear business? What does non-collinear mean? If I've got 3 points that are non-collinear, what's that saying? Not on the same line. Sure, and if we draw a triangle, that makes sense. I've got these 2 points, which we're going to call vertices. We'll get to some further vocabulary, but 2 of the corners of the triangle. I'll connect those with a side. And then if this is going to be a triangle, doesn't that third corner of the triangle, or the third vertex, have to be off of that line somewhere? If it's on the line, it's not a triangle. It's got to be maybe up there somewhere, for example. So I've got 3 pointy corners to that triangle. And so there we have it. I've got 3 segments joining 3 non-collinear points. And that's our triangle. Okay. Nothing you didn't already know. But now we've connected some specific math vocabulary to it. Okay, so classifying these things. Let's start off by classifying triangles by the sides of the triangle. What if we have all 3 sides that are the same length, all 3 sides that are congruent? Well, like this. You probably remember that we call that equilateral. Now, think about the name, equilateral. Equa means equal, right? And lateral, as we've already said, lateral just means side, so equal sides. So there's one classification by sides. If all 3 sides are congruent, it's equilateral. Well, what if 2 sides are congruent? Like so. Okay, do you remember what we call that? Isosceles, sure. Okay, so it's isosceles if we have 2 congruent sides. And then what if we have 3 oddball sides, none of which are congruent? This, yeah, maybe you saw it, maybe you did. That's the weird one. That's the scalene one. Okay, and that's going to look like sort of a bizarre oddball. All right. What if we classify by angles? Okay, well, let's take a triangle like this where all 3 of the angle measures, for example, look here, we have measure of angle CAB. So CAB, this one must be that angle right there, right? What's another name for that angle we could have? We could call it angle CAB. What else could we call it? Say it again. Oh, you're right. It is a cube. That's what we're getting at. What's another way we could name the angle? Not describe it. One way is we could call it angle CAB. What else could we call it?
BAC.
BAC, right? if we're going to name it with 3 points, as long as the vertex of the angle is in the middle, that's okay. Probably the easiest way to name that one would be what? Do we really need, I mean, is it ambiguous here? If I were to say, for example, angle A, is it confusing? There aren't any other angles we could confuse in this case with angle A, are there? Some cases there are. Like if I have two lines, let's say, that are intersecting, and the point of intersection is A, and that's B, and that's C. Well, now I can't really call it angle A, because angle A could be any one of those 4 angles, couldn't it? But in this case, there's only one angle down there at vertex A, so probably the easiest way to label this one, we could just call this the measure of angle A, right? And that's actually kind of important. We always want to do things in the simplest way we can. So anyway, if we line up, if we look at the measures of these 3 angles, one of them is 41.76, one of them 70.26, one of them is 67.97. Well, what do you notice about the sizes of those angles? They're all acute. They're all less than 90. So if all 3 angles in a triangle are acute, then it's an acute triangle. Okay, well, let's compare that to something different. What about, well, actually, this isn't so different. This could even be the same, couldn't it? There's a lot of overlap, you'll find. A lot of overlap in these classifications. We could classify one triangle as having a certain name if we're looking at the sides, and that same triangle could have a different name if we're looking at the angles, for example. Equiangular triangle. Just like we had an equilateral meant same sides, equiangular means same angles. So any triangle where we have 3 congruent angles, we're going to call an equiangular triangle. Okay. What else could we call this one? What if we knew this, for example? We could call it acute. Yeah, it is an acute triangle, absolutely. We know it's acute because going back to what we talked about, what you guys talked about in middle school, what is the sum of all the measures of the interior angles of a triangle? 180, sure, it's 180. So if all 3 of these add up to 180, and we're told that they're all 3 the same, they're all 3 congruent, what must the measure be? Sure. 180 divided by how many angles? 60, right? Because 180 divided by 3, they'd all have to be 60 if they're going to be the same and add up to 180. So that would be acute. We'll find later that any angle, or any triangle that is equiangular also has 3 congruent sides. And so what's the last thing we probably could say about this? If we know all 3 sides are congruent, it's also equilateral. Yeah, there's lots of ways we could describe this one. Okay, if we have one right angle, and let's indicate that. Remember, that means right angle. If I've got one right angle, then it's a right triangle. What do you know about the other 2 angles in that triangle? If one of them is a right triangle, is a right angle, I'm sorry, so it's 90 degrees, and they all add up to 180. What about the other 2? They have to be acute, don't they? Because combined, the other 2 have to add up to 90. So each one must be less than 90, right? Good. What if we have one big obtuse angle? There's my big obtuse angle. Well, that means it's bigger than 90, right? So if that's bigger than 90, then the other 2 angles combined have to be less than 90, don't they? Right? And so they must be acute. So if I have a single obtuse angle, it's an obtuse triangle. Okay. Parts of a triangle. Okay, let's look at the anatomy of a triangle here. We know that each of the 3 points joining the sides of a triangle is called a vertex. So there's vertex A, vertex B, vertex C. The plural is vertices. We don't say vertexes, we say vertices. Okay, so then we sort of also implied that the segments connecting the vertices are the sides of the triangle, right? So we've got vertices and sides for any triangle. If we want to be specific about, let's talk about the sides as compared to angle A. if we're focusing on angle A, then the sides that connect to angle A are adjacent sides. Adjacent just means next to. So they're next to or adjacent sides. The side that is clear on the other side of the triangle that's looking at angle A, or the side that angle A is looking at across the triangle, that's the opposite side. Okay? If we've got a right triangle specifically, well then instead of saying sides, we're going to actually identify the one side that is opposite the right angle, as we've talked about a little bit in chapter 3. The side that's opposite the right angle is the hypotenuse. That's a specific one. That's an important one. The other two sides that are adjacent to the right angle, that are touching it, are called the legs. So they get special names. Okay? Hypotenuse and legs. Oops. There we go. Okay, same thing for an isosceles triangle. We're going to be specific about it. Now we're going to say that the two sides that are congruent, we're going to call the legs of the isosceles triangle, and the one oddball that's different, we're going to call the base. So you can always imagine with an isosceles triangle, it's kind of good in geometry, I believe, to kind of get in the habit of just sort of twisting things around in your mind, and you get better at it. You can always imagine that you're going to take this isosceles triangle and twist it around and set it on a table on its base. So the base is always the horizontal part when you reconfigure it. You don't have to do that, but sometimes it's convenient. Yeah.
Are an isosceles triangle and a right triangle the same?
They could be, but they don't have to be. An isosceles, now what's the definition of an isosceles triangle again? It has two congruent sides, and the definition of a right triangle is a triangle with one right angle. So they might be the same, but in general they're probably not, but they could be. They could overlap. Well, actually, we'll see an example here pretty soon where they are the same. This one, right here. Identifying the parts of an isosceles triangle. So first, let's take into account that this is isosceles. Okay, triangle ABC is an isosceles right triangle. Why is it isosceles?
Because two sides are the same.
Yeah, because two sides are the same. So we can indicate that those two are congruent. Why is it a right triangle also? Because it's got a right angle. Sure. Okay. All right, good. So that's an overlapping definition. That's going to happen a lot.
So isosceles triangle has two of the same sides, right?
Yeah.
That's the definition?
Yep. Mm-hmm. And so what we find out then is that these are the two legs of the isosceles right triangle, and the base of the isosceles triangle in this case is also, it's the hypotenuse because it's a right triangle. Okay?
What makes it a right triangle?
The fact that it's got a right angle in it.
Okay.
Yeah. Okay, I didn't make this, I promise. A little goofy notation here, but we'll go with it. Using angle measures of triangles. So what this is getting at is that not only can we define or talk about the three angles that are on the inside of a triangle, we can also look at the angles that are on the outside, that are formed when we extend. For example, if I take this side AB, and I extend that as a ray. I'm going to start at A, and instead of stopping at B, I'm just going to keep going. Anytime I do that, anytime I convert the side of a triangle into a ray that goes forever, I'm going to create an exterior angle that is less than 180 degrees. I'm really going to create two exterior angles, but one of them is pretty boring. One of them is a straight angle that's 180 degrees. I don't care about that one. The one I'm interested in is the exterior angle that is less than 180, the angle that's formed between the extension of that side, the ray, and the adjacent side of the triangle. Okay? So now notice in this case that the three smiley faces are the interior angles, we would say, and the three hearts are the exterior angles. Okay, a very happy picture up here. Make sense? Okay. So for example, let's just I'm going to draw one of those. Let me go to. So for example, if I've got, let's do this. If I've got these three vertices of a triangle, A, B, and C. Yeah, I can connect those with regular sides. I can do that quite easily, not a big deal. But if I want to find an exterior angle, if I want to find exterior angle C, for example, I can find that in one of two ways, and I don't really care which one I use. I could either extend side BC as an infinite ray. That's fine. If I do that, now, do you see where exterior angle C is? This guy down here, isn't it? Right, this is the one we're talking about. This is the exterior angle. Or, I could do this. I could extend AC like so. Now, it doesn't matter, does it? How come it doesn't matter? They're the same, right? Either way I do it, whether I extend, if I make the blue extension or the black extension, look what I get. I'm going to get either that angle or that angle, but they're vertical angles, so they're congruent. It doesn't matter, right? So with each of the vertices on a triangle, it doesn't matter which one I extend to make the exterior angle, I'm going to get the same exterior angle no matter what. Yeah.
So both blue and black are the same angle, C?
Right. Those would both be considered exterior angle C,
What
either
about the
one.
one in the middle?
This is the interior angle.
No, the one in the middle between the blue and the black on the outside.
Oh, this one's nothing really. It's not. This is just a replica of that interior angle C because it's vertical angle without. But the exterior angles. Exterior angle for C could either be that one or that one. It's the same size, doesn't matter. Okay. Now, what can we do with these exterior angles? Well, there's a lot of stuff that eventually we'll do with them. But for now, here's one thing. Well, first of all, here's the exterior angle theorem. This is kind of an important theorem. We know, for example, in this case, that angle 1 is an exterior angle of this triangle. Right? I get it by extending the bottom side. Okay? One thing we know is that the measure of an exterior angle in a triangle is equal to the sum of the measures of the remote interior angles. Now that's kind of a mouthful. What did I just say there? The measure of the exterior angle, 1 in this case, is equal to the sums of the measures of the two interior angles that are remote, meaning they're not next to 1. They're not adjacent to 1. So the two that are far away in the triangle, if you add those measures up, they always equal the measure of the exterior angle. That can be useful to us. For example, what if we want to do something like this? Let's say we want to, here, let's do this. What if we want to solve for x in this case? Okay, and if we solve for x, by the way, we could fill in all of the angle measures there. We could what we say solve for the triangle. We could fill in all the angles. It'd be 2x plus 2 plus 65. Okay, how's that going to work? By that exterior angle theorem, what's the relationship between this exterior angle and the two remote interior angles?
Would it be x plus 65 in parentheses equals 2x plus 10?
Perfect. That's it, right? So we've got x plus 65 equals 2x plus 10. Now look what we did. We took a geometry concept, and now we've just got a simple algebra equation that we can solve. Right? We could subtract x from both sides, subtract 10 from both sides to isolate the x, and we get x equals 55. Now, if we wanted to, we could go back and fill in all the blanks. If x is 55, then look what that does for us. So we know this is 55 degrees. That's 65 degrees. If I plug 55 in there, 2 times 55 is 110 plus 10, 120. And so we could actually fill in that third interior angle also. What's one way that we know that third interior angle? Okay, yeah, because we know that 65 plus 55 plus that must equal 180, right? Because we know that the sum of all the measures of the interior angles is 180. So 180 minus 65 minus 55, that's subtracting 120. It's going to give me 60. What's maybe even an easier way? If I know that this one's 120.
It's a linear pair.
Yeah, sure. Yeah, this interior angle and the exterior angle that's adjacent to it are always going to be a linear pair. They add up to 180. So 180 minus 120, right? 180 minus that 120 is going to give me my 60. Yes?
Why are those angles different? They look exactly the same.
Well, okay, yeah, you're right. And they will. Remember that when we're looking at geometric figures, it doesn't matter what they look like. Always assume that they're not drawn to scale, that they're distorted. Okay. The only thing that matters is the given information. If there's marks made on there, like if I'm told that two things are congruent, that's I can rely on. If I'm told that that's 65 and that's x and that's, I can rely on that stuff. But whether it looks right doesn't matter. Always assume that the triangle is drawn poorly, that it's distorted, or the quadrilateral, or the angle, or whatever. Just assume that they're not drawn to scale. Okay, moving on. How could we find the angle measure here? Okay.
Can't you just plug in that's 90 because right?
Okay, now let's assume, yeah. Now let's actually assume here, and I need to include that. Say we do know this is a right angle, a right triangle. How could I find the angle measures of the other two sides? What do we know about this? What do you know about once again, the measures of the three interior angles of a triangle always add up to 180. Okay, so now what if it's a right triangle? If it's a right triangle, you know that one angle always is going to comprise half of that 180, right? So if it's a right triangle, the other two angles must always add up to 90, yeah, right? The two acute angles in a right triangle are always complementary, okay? So we could easily solve this by just setting, x plus 2x equals, yeah. So x plus 2x equals 90, 3x equals 90, so what's x? 30. So then that means this is 30 degrees and that's 60 degrees, so it's a 30, 60, 90 triangle. Right. Okay. Okay, now there's a little review of some triangle stuff. I want to go one step further today, and I normally wouldn't do this, but you got to bear with me today. I apologize. Okay, I want to look at some properties of congruence in triangles. And you'll be fine with this, I promise you. Identify congruent figures and corresponding parts. We're going to be able to prove that two triangles are congruent. Okay, so first of all, what does it mean if we say that two geometric figures are congruent? There's two parts of that definition. Two geometric things or figures are congruent if they are the same shape and size. Okay, now later on in geometry, we'll look at some cases where two objects might have the same shape but be different sizes. For example, we might have two equilateral triangles, and one of them is small and one of them is big. Okay, they have the same shape, but one is small and one is big. In that case, we won't say they're congruent. We'll say they're similar triangles, not congruent triangles. But if they're the same shape and the same size, they're congruent. For example, the three red quadrilaterals are congruent. And the way you can kind of tell, the visual test you can always make is if I cut this one out in cardboard, could I pick it up and reorient it so I could set it down on top of this one, for example, and have it overlap perfectly? If the answer is yes, then they're congruent. If the answer is no, then they're not congruent. Okay? So here's an important point we got to make about congruency. If two figures are the same shape and the same size, if they're congruent, then you get a lot of information with that. You know that there is going to be a correspondence between all of the angles and the sides such that each corresponding angle is congruent between the two figures and each corresponding side is congruent. So each individual part, another way of summarizing that, each individual part of one figure, if it's congruent to another figure, has an individual part of the other figure that has to be the same, right? Each side goes with a corresponding side, each angle goes with a corresponding angle. So for example, in these, let's look at this congruence relationship. I've got two congruent triangles. Now notice here that angle B is congruent to angle Q, angle A is congruent to angle P, and angle C is congruent to angle R, right? Also, side AB is congruent to side PQ, side BC is congruent to side QR, and side AC is congruent to side PR. Okay? So because all of the angles are congruent, all the corresponding angles are congruent, and all of the corresponding sides are congruent. In other words, would you agree that if I pick this triangle up and set it down on top of this one, A goes with P, B goes with Q, etc., right? You can, right now, this time we know because I've got those congruence marks on there that are telling us for sure they are congruent. Not just because they look congruent, but because I can see that that's a single congruence dash with a single congruence dash means, that's telling me that is the same as that. Okay. Here's the important thing I want to get to though. If we can make all these correlations, right? If we can link all three angles to these three angles, each of these three sides to these three sides, then I have to be careful how I write the congruence relationship between the triangles. There's more than one way to do it, but what you have to do is you have to link up the corresponding vertices have to go in the same order when I write the triangles. So for example, you finish this for me. If I want to say that triangle ABC is congruent, so this triangle is congruent to this one, what's the order in which I have to include the vertices on this triangle? PQR. Because P goes with A, Q goes with B, R goes with C. Now, once I've done that, that gives me a ton of information. I can see then, just from this congruence statement, I can see that angle A is congruent to angle P. Angle B is congruent to angle Q. Angle C is congruent to angle R. I can even go further than that. I could say that side AB must be congruent to side PQ. Right? I can say also, side BC must be congruent to side QR because they occupy the same places in that congruence statement. See how that works? Now, how else could I say this congruence? What if I said triangle BAC? How would I have to write the other one? Q goes with B, A goes with P, so Q, P, and then C goes with R. I have to write it like that. That's also correct, though. Okay? All right. Okay, so write this one. Just try this one on your own real quick. Write a congruent statement here for those two triangles. Be careful. Yeah.
Are they congruent?
They are. But you may have to twist them around a little bit. Now let's see here. Which angle is congruent to angle E? Okay, S. So E and S go together. Let's change colors. Angle D goes with which one? R. Yeah, and how do you know that? Yeah, we have two congruence arcs for those two. And then finally, F is congruent to T. So now we'll just match those up by vertex, right? So we must have triangle EDF would be, if I'm going red, green, purple, that would be SRT, right? I've got to line up the corresponding angles there, okay? So DEF would go with RST. Okay. And then from that tells us all the other stuff. It tells us that angle D is congruent to angle R, for example. We can see all the other stuff there also. DE must go with, side DE must go with side RS. Side DF must go with side RT. I can just match up the corresponding vertices, right? Okay, now how about using properties of congruence to solve for x? Okay, try this. Okay, they're telling us here that figure NPLM is congruent to figure EFGH. Okay, so how could we find the value of x? If that's true, now look at the x over here. Here's x. Right, x appears to be 2x minus 3 is the length of what side of this triangle? Which side? No. 2x minus 3 meters is the length of, what's that side? GH, right? Okay, so if that's side GH, well, GH goes with LM, right? So we can match those two up. So then this length must equal that length, right? We can set the corresponding parts equal to each other. Yeah.
Is it possible for it to equal like a 0.5 or a half?
Sure. Yeah. Yeah, so let's see what happens if we set those equal to each other. If 8 is equal to 2x minus 3, then, you know, all we have to do is just add 3 to both sides, divide by 2, and so x equals 11 halves, or 5.5. Okay? So now, how would we do the same kind of thing? Let's try again here. Okay, try again. Oops. Okay, solve for y. Okay, where's the y?
Is it between E and B?
Yeah, it looks like y is part of an angle. Angle E has a measure of 7y plus 9 degrees. So angle E goes with which angle? Yeah, it's got to go with n, doesn't it? So E and n are congruent, so then it looks like 72 must equal 7y plus 9, right? So we'll just set those equal and solve for y. Subtract 9 from both sides, divide by 7, y is 9. We got it. Okay? Okay, we're getting there. I want to look at... Okay, real quick, this one, here's another theorem, third angles theorem. These are all included on your sheet, by the way. Third angles theorem is really obvious. Doesn't it just make sense that if any two angles of one triangle are congruent to two angles of another triangle, then don't the third angles also have to be congruent? It makes sense, right? And the way we can always think of that is, if A and B are congruent to D and E, then there's 180 degrees in both of those two triangles. So in both cases, there must be the same amount left over for that third angle, right? Okay. So how can we do this then real quick? Let's just zip through this. Find the value of x. Well, if I know, these got kind of shifted here a little bit, but if I know that angle S is congruent to angle L and angle R is congruent to angle N, then that also means that the other two angles are congruent, right? Doesn't that make sense? So that means that this angle up here must be, and this is a little bit goofy, but that's supposed to be the measure of that third angle. Right, so up here we must have 2x plus 30, and then I know that all three of those have to add up to 180, right? So I can say 180 equals 55 plus 65 plus 2x plus 30, solve for x. No big deal. Okay? I'll let you guys look through that one. That's not that big a deal. This is the one I kind of wanted to get to. These two.
Why was Big still in here?
Oh, he just
Observing?
no, he just kind of wants to see what's going on in class. Okay, so let's take a look at this now. We're not going to do this one formally. Let's just talk through it though. These last two examples. You got to really super focus on the last two because these are the two that are a little bit harder. Decide whether the triangles are congruent and justify your reasoning. Well, they are congruent, but how can we show that they're congruent? Now look what we're given here. We're given that side RQ is congruent to side MQ, right? Those two sides are congruent. Those two sides are congruent, and those two sides are congruent. So we've got all three pairs of corresponding sides are congruent. That's good. Now, if we could just show that all three pairs of corresponding angles were congruent, then by the definition of congruence, if all the corresponding parts of those two triangles are congruent, they're congruent. That's what congruence means, right? Well, look what we got here now. 92 and 92. Those two angles are congruent for sure. You see any other congruent angles? Okay. Yeah. RQP and MQN. These two angles right here, right? Now, why are those two congruent? What's the reason for that? We can see that they are, but what's our reason? Yes, sir.
Because the four lines on the side almost equal the same.
Okay, but what's our, if we had to look at our list, what's the reason? What relationship do they have which shows that they're congruent? Oh, I think I heard it. Vertical angles. Yeah, they're vertical angles. Yeah. So then we know those two are vertical angles, so they're congruent. And now, by the third angles theorem we just talked about, if those two are congruent and those two are congruent, then the third angles must also be congruent. And so now they're congruent. All the parts are congruent, right? Okay, we out here at 40?
Yeah.
Let's stop there. That'll.